Good morning friends, welcome in the today's session. Today we will see or we will start our first unit, that is waves. Yesterday we discussed about the syllabus. As we have seen in the last lecture, in yesterday's lecture, we have 4 units, and among them we will start today the first unit, that is waves. Okay, the very first article in this unit is wave velocity and particle velocity. Yes, you can see on the screen the first article, which is shown by the green color, that is wave velocity and particle velocity. So first of all, wave is what? Wave, most of the times we think that yes, if wave is traveling in a particular direction, all the particles of the medium are also traveling in the same direction. This was the misconception in our mind when we see any wave. So we think that yes, the wave is moving, that means what, all the particle of the medium also moving in the same direction. But actually this is not the condition, this is not the case, where the particles are moving with the same velocity, or sorry, the particles are moving with a different velocity, and wave is also moving with the different velocity, and that's what we have to see in today's class. Okay, so how the particles are moving with different velocity and wave is moving different velocity, or their direction is same, or their speed is same, and whatever it may be, everything we will see in this particular class. Okay, now look into the diagram which is shown on the screen. You can see a particle is moving, or we have drawn one wave which is along the positive x direction. So consider any simple harmonic motion of a particle, and the wave is moving along or traveling along positive x direction as shown in the diagram. Now when we say that the particle is performing simple harmonic motion, yes, we have considered the SHM, simple harmonic motion. When particle is performing simple harmonic motion, that means particle is going to extreme position, or we can say it will start from the mean position, then it will go to the one extreme position, again will come to the mean position, and again it will go to the another extreme position. We know that this is what we call the simple harmonic motion, and where the displacement or the acceleration is always directly proportional to the displacement. That is what we call simple harmonic motion. We have seen this simple harmonic motion in the last semester mechanics. Okay, now here what I am saying, dark wave, we can say we have drawn two different waves in the diagram. One is having a little bit dark ink, and another is faint, or we can say it as dotted. So let us consider the dark line curve represents the displacement of a particle at the time t1, and the curve which is shown by the dotted line is the displacement of particle but at a time t2. That means what, we have to consider two time instants. Yes, let us consider the particle is moving along positive, or the wave is moving along positive x direction at a time t1, means I am observing the wave which is moving along positive x direction at a two different time instances. One is at t1 and another is at t2. So the t1 instant is shown by the dark line, and t2 instant is shown in the dotted line. Okay, now you can see that the origin we have shown by the point O. Then after some time, yes, the dark line meets to the x axis, that point is A, and the dotted line meets to the x axis, that is what, or dotted curve reaches, or what we can say cuts to the x axis, that point is shown by the capital B. Okay, now that small ABC, what are that, we will see in the next slide, don't worry. So first of all, what we have to say here, yes, wave is moving along positive x direction, but the particles are moving along y direction, even though the y direction is not shown in the diagram, but yes, the vertical axis is y axis. Yes, everybody know. So the particles are moving along y axis while the wave is propagating along x axis, or we can say, in other words, the particles are taking, or particles are performing simple harmonic motion along y direction, and wave is propagating along x direction. Yes, right. Now what we have considered, two time instances at t1 and t2. Darken is for the time t1 instant, and the dotted line is for the time t2 instant. Now what we will see in the next slide, yes, the same diagram, little bit zoom. So what we have seen, let us consider now distance A from O be x1. Okay, we'll name these two distances x1 and x2. That means from O, the first time instant wave cuts to the x-axis at point A, that distance OA we will name it as x1. It is not shown in the diagram, but yes, we have to consider. And the distance OB, yes, that means what, the second time instant wave, that is dotted wave, cuts to the x-axis, position axis at point B. So that distance from the O will be x2, where the displacement of the particle is 0 at t1 and t2 respectively. The line, last line shown on the or you can see on this particular slide is what, where the displacement of the particle is 0 at time t1 and t2 respectively. So what is that? Because see, when particle starts from O, now let us consider, where I will show you, the particle is starting from this point, yes, the particle is starting from this point and it reaches, yes, it reaches to this point, again it reaches to this point. Now see, at point C, yes, at point C the particle is having maximum displacement. At point O the displacement will be, or the displacement was 0. Slowly particle is moving along the curve C, O, then small a, then C, then again capital A, right. Now see, this particular half curve from upper side, which shows that particle starts from the 0 displacement at point O, what we can say in simple language, that is mean position. Yes, it goes to the C. So C will be, or C is the point where the particle is performing maximum displacement, or the particle is performing a simple harmonic motion with maximum displacement. Now particle comes to point A. When particle comes to point A, capital A, I am saying capital A, when particle comes to the capital A point, then that is what, the displacement becomes 0. Displacement becomes 0. That's what is the last line, the particle displacement at t1 and t2. And at t2 again, now look at the second curve, that is dotted curve. So the dotted curve meets to the x-axis at what point? At point capital B here. Yes, so there also the displacement is 0. At these points, top points, the displacement is maximum, but when the curve meets to the x-axis, the displacements will be 0. That's why we have written the last line, that is displacement will be 0 at t1 and t2 respectively. Okay, so in this slide what we have considered? Only we have considered the distance OA is x1 and distance OB is x2. Okay, now go to the next slide, again the same diagram, because everywhere you need to observe the diagram. That's why I have put this diagram on every slide. Okay, now see, we have to do some little bit mathematical calculations to find the particle velocity and the wave velocity. So what we will consider? The displacement equation. This equation might be familiar with you. The displacement equation, y is equal to a sine 2 pi by lambda Vt1 minus x1. Yes, this equation you have seen in simple harmonic motion chapter in 12th, as well as we have seen in the first year also. Yes, a sine 2 pi by lambda Vt1 minus x1. Any wave, or moreover the simple harmonic wave or the simple harmonic motion displacement can be represented mathematically by using this equation, y is equal to a sine, actually it is omega t minus k, but yes, omega is equal to 2 pi nu by lambda. That's why we have taken that 2 pi by lambda outside, and therefore a sine 2 pi by lambda Vt1 minus x1. Now similarly we have written the displacement for the second time instant. Yes, you might get confused at this point, but don't worry, y is equal to a sine 2 pi by lambda Vt1 minus x1. This equation is for the first wave, that is for time instant t1, and again the displacement will be same. Yes, at a time t2, this will be the equation, y is equal to a sine 2 pi by lambda Vt2 minus x1. Vt2 minus x1. Here t2 means time instant second, and here t1, that means time instance first, and x1 and x2 already we have considered. OA is x1 and OB is x2, but the displacement at both the time will be same. Therefore we have written y is equal to both equations. Now forget about the y, both sides are equal, because left hand side y and right hand side a sine 2 pi by lambda Vt1 minus x1, and second equation a sine 2 pi by lambda Vt2 minus x2. Now both the equations are, equate both the equations, small a will get cancelled. Now if we take the sine inverse on both sides at this step, what they have done? Yes, what we have done here, Yes, we have taken the sine inverse on both the sides. Sine inverse on both the sides. If we take the sine inverse on both sides, what happens? Sine get cancelled. Next, 2 pi by lambda on right side gets cancelled with the 2 pi by lambda on left side. Then what remains? Only Vt1 minus x1. I am talking about this step. What is that? Vt1 minus x1 is equal to T2 minus x2. Okay. Now now what we have to do, just take the vv terms to the left side and xx terms to the right side. If we take the vv terms, that means already vt1, or we can take a vv terms to the right side, vt2, and this vt1 goes to the right side, becomes minus, that means vt2 minus vt1, and this x2, negative x2, goes to the left side, becomes positive, that's why x2 minus x1. Okay, right? These are the simple calculations you can do at on your paper also. Okay, simple. Take the vv terms one side and xx term one side, and because vt2 minus vt1, we can take now v common. If we take the v common, then what it gets? V in bracket t2 minus t1 is equal to x2 minus x1. Okay, you have to perform these calculations in your notebook. Okay, so here some steps are ignored, but these are the small steps, easy steps, you can do it. Okay, now what we got? The equation, next equation, v in bracket t2 minus t1 is equal to x2 minus x1. Now again v in bracket t2 minus t1, just take to the other side, and therefore we got v is equal to x2 minus x1 was already to the right side. Now divide by, because t2 minus t1 bracket was in multiplication to the v, now it goes to the other side, now it will be in division. So it is v is equal to x2 minus x1 divided by t2 minus t1. And yes, what is x2 minus x1? This is what? Small change in the displacement. What is t2 minus t1? This is what? Small instance time t, right? Small instance, that's why we will call it as delta t. Here x2 minus x1, even though in the diagram we have taken these are the longer distance, but actually this is very fractional distance, and that's why we name it as delta x. X2 minus x1 is equal to delta x, and t2 minus t1 is equal to delta t. So finally what we got is v is equal to delta x by delta t. Okay, right? Now we will go to the next slide. Yes. So if we look at the diagram, I will just take the previous slide one more time. Okay, yes, see. Okay, now see here what we are saying, that the particle is moving along this y direction, vertical direction, while the wave is propagating along x direction. That means what? Whatever may be this v is not the particle velocity. This velocity, right? This velocity is wave velocity. That means v is the velocity with which wave is traveling along x direction. V is the velocity with which wave is traveling along x direction. That is not particle velocity, but we know that our particles are performing simple harmonic motion along which direction? Y direction. Yes. Now when I want to represent, or I want to write the equation for particle velocity, let us consider u is a particle velocity. That is the notation for particle velocity. Capital U is the particle velocity, and in general how to write velocity? Rate of change of displacement per unit time, what we call is velocity. So how will be the displacement along y direction? dy, or simply if y is the displacement along y direction, then its rate of change with respect to time is dy by dt. So particle is performing simple harmonic motion along y direction, and that's why here we have written directly particle velocity. Particle velocity is equal to dy by dt. Actually it is delta y, because yes, we are talking about the fractional displacement, fractional time instance, that's why delta. So finally we will talk about that delta and d, what will be the difference, but right now we will see particle velocity u is equal to delta y by delta t. I hope you are getting this, because particle is only performing simple harmonic motion along y direction. That's why we cannot take delta x by delta t. Delta x by delta t is again velocity, because x is also displacement, but yes, it is moving along positive x direction. Delta x is also a fractional displacement, but it is what? Along positive x direction. And who is moving along the positive x direction? Not our particles. Who is moving? Wave is moving. That's why that will be the wave velocity v. But now for the particles, particles are performing simple harmonic motion along y direction. That's why particle velocity u is equal to delta y by delta t. Now what is that delta, and we have written where delta y is a distance moved by the particle in a small interval of time delta t. Yes, you got this. Now during the time delta t, the wave goes from A to B. The position of particle downs from C to B. Yes, why this statement is there? For this we have to go again to the diagram. Now look at the diagram. What is written? During the time delta t, wave goes from small a to b. Now look at this, wave goes from small a to b. Yes, wave goes from small a to b. But what happens? The particle moved from c to b, small c to small b. Yes, you are getting this. Wave is moving like this, but particle is moving like this. Yes, wave goes from A to B, while particle comes from C to B. That is what we have written in that statement, where or during the time delta t, wave goes from A to B and the position of the particle downs from C to B. Yes, because particle comes down, that's why down C to B, or we can say particle changes the position from C to B. Now hence AB is equal to delta x. Why we are saying AB is equal to delta x? Yes, because yes, OA we name it as x1, but AB is the displacement or whatever may be the distance. It is along what? Which direction? X direction. That's why we name it as delta x, fractional distance, small distance. That's why AB is a delta x. And CB, can we name it as CB? CB is what? Delta y, because this is what? Displacement along y direction. This is displacement along y direction. That's why CB will be delta y, and while AB will be delta x. So hence here we have written AB is equal to delta x. But delta x is what? We have just seen in this equation. See at this equation, delta x. From this equation, can I write delta x is equal to v into delta t? Can I write delta x is equal to v into delta t? Yes. So put there delta x is equal to v into delta t. We have used that equation, wave velocity v. Delta x is equal to, actually we got v is equal to delta x by delta t. From that we have written delta x is equal to v into delta t. Okay, and BC is equal to, BC, again we will look at the diagram. What is BC or CB? BC or CB, yes, look at this, it is changing along y direction, and that's why it is delta y. And delta y from this equation, again what is delta y from this equation? Delta y will be u into delta t, and that's what we have written here. So what we got? Two equations, delta x is equal to v into delta t and delta y is equal to u into delta t. But moreover, what are those? AB and BC. AB and BC. Now let us divide this BC by AB. Okay, you can take it as equation number 1 and equation number 2, and we can say divide equation 2 by 1. So here I am directly saying divide this BC by AB, or divide this equation by this equation. Okay, now this equation left hand side BC divided by AB. Now see, look at this, BC divided by AB, BC divided by AB. And what is BC? BC is what? Delta y, that is u into delta t. BC is what? Delta y, that is u into delta t. Here we have substituted. Now what is AB? AB is delta x, and that is equal to v into delta t. AB is delta x, and that is equal to v into delta t. Yes, two steps they have merged together. We have merged together. No worries. You can make these are two separate steps. It is up to you. The calculation part is up to you. Okay, you can combine some steps, you can skip one any simple step, or you can merge any two step, or we can distribute, or you can make it as long as you want. But the thing is what, you must understood it what exactly happens, right? Now see, now forget about BC and AB. So to this side, delta t gets cancelled. Where what remains? Here u by v, and to this side delta y by delta x, delta y by delta x. So finally what we got, this equation u by v is equal to delta y by delta x. Now yes, so I told you already what is this delta y and dy. Okay, delta y is very small fractional distance, okay, and if we want to talk about the whole slope of the curve, then we have to take it as d. And moreover, mathematical, this is completely a mathematical term, mathematics students might have known this. So limit delta x tends to 0, delta y by delta x becomes dy by dx, delta y by dx becomes, oh sorry, delta y by delta x becomes dy by dx, and that is what slope of the displacement curve, because whatever we have shown in these both the diagrams or all diagrams, these are what, these are the displacement curves. So its slope means dy by dx, right? So finally what we got, dy by dx, and instead of this delta y by delta x, finally we will substitute here dy by dx, and this equation comes, that is left hand side as it is, u by v is equal to, instead of delta y by delta x, just put dy by dx, and now yes, bring this v to this side, and it becomes u is equal to v into dy by dx, u is equal to v into dy by dx. Okay, this is what our final equation, and this equation shows what, this equation shows what is that, yes, this equation, what is u, if you remember initially, u is a particle velocity here, yes, u is a particle velocity. What is v, v is a wave velocity, because see here v is equal to delta x by delta t. So v is a wave velocity while u is a particle velocity, and what we got, their relation is this much, u is equal to v into dy by dx. That means what, now if I want to write in terms of words final equation, this equation, what, how can we write, u is particle velocity, and therefore we have written here like this, the particle velocity is equal to, what is v, v is wave velocity into, what is that, dy by dx, it is simply the slope of the displacement curve. That means particle velocity is equal to, what we can write finally, particle velocity is equal to wave velocity into slope of the displacement curve. So I hope this is clear to you. Now this is the end of this particular article, wave velocity and particle velocity. Now onwards, if somebody asks you what is particle velocity and wave velocity, or if particle velocity and wave velocity are same, so what is your answer? Yes, it is not same, they are not same. Particle velocity is different and wave velocity is different. And how they are related, finally particle velocity is equal to wave velocity into slope of displacement curve. This is what the relation between particle velocity and wave velocity. Sometimes it can be, or this article can be written as the relation between particle velocity and wave velocity, right? So this is what the end of this article and this video. Thank you.